Okay, guys, we'll carry on with the conditional expectation and move on to Martingale. That's that. We start the recording now. I think it's the two guys will come to me and then one more person. You can, if you're okay with it, you can get on to 5 minutes. Okay, so let's go on to conditional expectations. So we know we're given the space, you have P. You have a sub sigma is the G is the is G measurable and it indicates like X. And that would be the last time we proved its existence, we proved its uniqueness, and then we talked about some properties like linearity,
A, the bigger sigma is greater.
what's that?
For all A, the bigger sigma is
Smaller. So X is not measurable here.
Yes.
Yeah, we think of X as a function of Y and Z, and this only depends upon Y. This is a function of Y. Okay, so one thing was, I guess what happens now in a setting where we are already given that, okay, suppose I tell you that X and Y have a joint density function. We're going back to elementary probability. Right? So we want to say that they're consistent with the elementary probability, right? So we start off by saying, okay, the measure is assigned as follows. This property is there. And then from this, you can easily see that this automatically implies that h of respective value h x y, whenever it exists, it will be right. And this we know because it's true for indicator functions, h, simple functions, and by limit non-negative functions, and more general. Okay, so this is also this is specified in this follows. Okay, that's good to know. Now we want to find, we want to define E of x given y in this setting, a random variable of x given y. So what's a candidate?
This smaller sigma is the sigma represented.
Yeah, so you have to integrate like y, that's true. But you have a specific candidate. I mean, this is all elementary probability now. So what's the conditional expectation that is?
Conditional
Yes. So at this place where y omega is equal to y, we want this to be equal to g of y, which is defined. Does it come here? That's a different condition probability. So you'd want that to be true even now, right? This is x, y. And we want to know what the margin is. It's just like the joint distribution of y. Okay. So what we'll do is we'll define the random variable g of y. Now we're keeping this random there. G of y is this. And now we want to show that, okay, integral g of y. And what we want to show is this. What we want to show is that g of y omega dt over a is equal to integral x dt over a for a in sigma g. A is in sigma y, I guess, right? For another number. So this should be true. So let's just simplify it. And now we know because we have a joint distribution function. Okay. So we know because we're joint distribution is the same as g of y function of y, right? So f y is in okay. Any function of y will have this property because of the joint distribution. We just showed it. Now this can be simplified as y in a x in r conditional distribution. I'm just spelling this out basically, and might as well look it up. That's by Fibonacci eventually. It's just a. I guess in the function of y. That's exactly equal to here. So x dt over a versus b x into the joint product with the whole region, which is y lying in a and x lying in r. So if I should call it. No. So that's what that's exactly equal to. Okay. So good. So conditional expectation generalizes. Other part we didn't quite do last time was it's an important property, so I just mentioned it. And suppose we have, let's say, sigma of x and let's say h here, they are independent of g. So these two sigma algebras, or you could say sigma algebra that includes these two is independent of g. Then you want to say that e of x given h and g. What should this be?
E of x, E of h.
E of x given h, right? Yeah. Because g is independent, so there's no information there. So you want to show this. And this will turn out to be true, of course. But again, the way you started it is that you show the simple things. And it's not always the same machinery, so just be careful with this outline how one will do this. So what do we want to say? We want to say that on the sets which belong to sigma algebra of sigma x and h, on the sets which belong to sigma algebra of g and h, right? On these sets, this guy integrates like x. That's what we would say. So we take what we do is let's take a set here G A, let's call it. We want to say that E of x given h is equal to that's what we want. And that proves for us that this guy is because it's certainly sigma, this sigma measurable. So this is the right function. That's what we want to show. The way we do this is as follows. We show that this is true for a pi system. And there are two measures which agree on a pi system, so they'll agree on the sigma algebra containing the pi system. So that's another tool to keep in mind. So the pi system is going to be G intersection. You can convince yourself that the intersection of these two sigma algebra is a pi system. If I do A cross B from here and something else, then the intersection is also for the same point. So G, yeah, I guess, yeah, maybe.
The intersection would be a sigma algebra.
Yeah, no, that's bad notation. I guess what I want to say is product form. I want to collect all sets of the form. I don't have a notation for it right now. I guess I want to collect all sets of form A intersection B. Then A is in G and B is in H. No, it's right. It's a sigma algebra. That's fine. And it just has to be a pi system, I guess.
Yes, pi system is close to the intersection.
Yeah.
No,
but these collection is not a sigma algebra right now.
Yeah, it is not closed under complement.
Yeah, so this is not a sigma algebra right now. So I just look at these things. Okay. And it's a pi system. And sigma algebra containing these sets is sigma algebra containing both G and H. So that's a union of sigma algebra, which is a union of G and H. Sigma algebra which contains union of G and H. That's not intersection. Yeah. I mean, this is not equal to G intersection H. It's not equal. So, and this now I'm going to write. So let's go and look at this guy, for example. Intersection X, B, P. A intersection B.
So I'm taking the union of, I didn't get the set properly. That is not always fine.
Well, this cell is well defined, right? I just take A in G and B in H.
Yeah, you're taking the elements.
Yeah.
And then you're taking the union also.
No, I'm just collecting A intersection B.
Yes.
Intersection. I just collect all these things. It's a pi system. Pi system means if I have two sets in this collection, then there is intersection also wanted in this collection.
So G intersection H is a subset of this.
G intersection H is probably a subset of this. Well, in the sense that it's a subset of this. That's right. Yeah, but this is bigger.
With both G and H are subset of this.
Yeah, for example, I see the tree. Is it one here?
This one.
It's one.
So this is a bigger set than G and H.
That's good. Yes. Okay. So now let's see. So we're going to write this as B x indicator A dp, right? A is in G. Now A is independent of x. This is equal to P of A integral B x dp. Okay. And that's B is in H. So this is equal to P of A x given H. Right. And that's equal to x given H A section B dp. Right, because I can again bring A here as indicator function, and by independence I get this equal to this. But E of x given H is also independent of I of A. Function of H, right? That's how we define it. Okay, so what we have then is that this guy agrees with this guy. You have to measure this. Again, we just take x to be non-negative. We give it non-negative, it will separately for x plus x. So these two are non-negative measures which agree with each other on the pi system, and hence they agree on the sigma integral which contains the pi system. That's it. Okay. So now let's do function. So not enough background so far. Now we start doing interesting things in this course. We'll do Martingales now. And I think the way we'll do this is we'll do Martingales first, then we'll do running motion, then we'll do large deviations. In between, Shubhadra will take 2 lectures on reconvergence. So that should go a long way. I'll give 1 lecture next week. Shubhadra will give 1 lecture next week. So next week there'll be 1 lecture only because it's only on Friday. No lecture that day. And then week after that on Friday and Saturday, I'll send you a link. I'll be organizing a workshop on learning theory in Ashoka. So I would just expect this, at least for the kind of mandate that my tutorial is part of this course.
Yeah, on Zoom.
Huh? It'll be on Zoom, yeah. It'll be on learning theory. But other events are more interesting. So I request you can consider attending those. There's just a few more, and there's one more.
What you are taking in the course?
Huh?
In the,
I'll be giving a 2.5 hour tutorial on learning theory on bandits.
okay.
But I think Praneet Netrapalli will be talking about deep dive into machine learning. So 2.5 hours of that. And then Prateek Jain is giving a talk, he's from Google Research. Devagat Shah is giving a talk, he's from MIT. And Aditya Nori is in Microsoft Research in Cambridge, UK. And he'll be talking with healthcare and machine learning. And then Sunita Saraogi at IT Bombay. She's kind of much more into applied world of machine learning. So you get a much bigger flavor of different activities. Those are the talks. It's Friday and Saturday. But the other reason I mentioned that is that on that Friday also we will not have a lecture.
What is that?
26th, 25th, sorry, 25th. So that's good news. Then there'll be a Wednesday after that. And then we should have an exam, I guess. A midterm will have that time. So that's further good news. And then after that, we'll come back and do all the other things. Now it's a little tricky because we started on January 26th, so we started late, right? I mean, maybe what we can do if you allow me is, some lectures, because we want to finish by, when do you want to finish by? Do you have a sense?
Mid-May or something.
Mid-May. So I definitely want to finish by mid-May, the week after. So what we can do maybe is let's do the midterm on a non-lecture time, so we can still have a lecture. Okay. So now when do we have the midterm? I'll tell you what, let's have a midterm on the same Wednesday in the morning. That way when you come to the class, you already get everything. So you kind of,
Yeah, I have a class.
Or you have this, but just one class, right? So you can work on that or.
Or super early in the morning would be. Even earlier in the
Yeah,
morning.
that's it, yeah.
6 o'clock.
That's when I like to stay, yeah. I wish I had that. But what are the other time slots are you going to give to us?
Taking Sunday.
No, 7 o'clock.
Taking Sunday.
When is your this machine, this 9:30 to 11? See, our lecture is 4 to 5:30, right?
Yes.
So
So
you can
between
still-
it is, between that also it is.
Oh, there's another lecture.
No.
So that's
Can you take it on Saturday?
no, I don't want to push it so far. That's the thing. Yeah. That's why I want to have it before. I think before the lecture, maybe. Let's
Or evening, any day would be.
So maybe Tuesday evening.
Tuesday. Can you?
Huh?
Tuesday is fine. Tuesday is fine.
Tuesday, any evening, there in the classes. 25th and 26th is the running.
Yeah, yeah. 28th, I'm going to be in Delhi. So 29th is what I'm saying right now. So let's have an exam on 29th evening. Huh?
Evening.
So maybe around 5 p.m.
5, 6. Yeah.
What suits you? Otherwise, fine. I'm okay. Fine.
4 to 5:30 is information theory will be moving.
Is anyone taking that?
Oh, yes, yes.
So Praveen, I guess Shantanu will need to be informed.
Yeah, yes, sir.
Yeah, so we'll have this exam then on 29th.
Yeah, I'm fit.
And we'll have to see how to. Anyway, sorry. So that's the plan. And then, then we still have like a month and a half.
So it will be an in-person exam or online?
In-person exam. Is it the first in-person exam after a long time or?
Should be in like since 2020.
Can you do open book notes or something like that?
Everything I do know. Yeah.
That means it will be a difficulty level is like,
Yeah, open book never helps.
don't put open questions. That's
Well, the thing is that in such exam, you just don't give enough time for a person to go through the book. So that's what I need to do. No, it should be okay. Chalo, Martingales, yeah. What do we know about Martingales so far? You've seen it somewhere?
it's present.
Hmm?
It depends on the past information on the present information.
E of xt plus ungiven xt equal to xt.
Yeah.
And probability is less than infinity.
Probabilities.
Xt less than infinity is 1.
So that something stronger than that. Expected value of x.
Yes.
I couldn't show that. What does Martingale stand for in English? Do you know?
Gambling.
Martingale strategy. Yeah. And do you know some other meanings of Martingale? So you've seen the, let's say in Hindi, lagam on a ghoda, right? So from the saddle it's tied to their nose. And that keeps the horse kind of balanced. So that's called a martingale. And that's probably where the name came from. Just keeping things in balance this time. But in gambling, the martingale strategy is what we discussed earlier, which is that you bet 1 rupee, then you lose it, you bet 2 rupees, then keep on doubling. So for sure, one big result we'll probably do today or maybe early next time is that under mild assumptions, you cannot come up with a clever strategy, so you do better than the other player in a fair game. So if on average you're going to not win, you're going to keep it in the amount of winning will be 0, then you can't say, okay, my strategy is that as soon as I win 100 rupees, I'll leave the place. Or as soon as I lose so much, I'll leave the place. Or as soon as I either win 100 rupees and play 50 games, after that I leave the game. All those things on average will not benefit you. So that's a big theorem. Martingale's stopping time theorem. It's kind of a revelation in gambling, right? People always try to come up with the strategy that if I follow my strategy, I'll always win. But it's a thing like that can't be. So it's one of the theorems you hope to see. But Martingale intuitively at least is okay as I should have said. It's E of xn given everything x1 to xn minus 1. That should be equal to xn minus 1. So on average, you've not changed. Or if you look at your increment, given x1 to xn. That's equal to 0. This is a change, right? This is a bet you place in the amount you win or lose. That on average remains 0. So if that's true for a stochastic process with some mild conditions which I'll give later, then you have a martingale.
It would be also a larger filtration also.
Yeah, it's all that I'll discuss in a moment. I just want to motivate things right now. Right. And no matter where you go, x1 for every x1 to xn minus 1 is true. But every sample is not very good. So enormously powerful tool. It's a very simple definition. It turns out you can always play around with random variables to construct some martingales. You can subtract something, add something. With all of that, you can construct martingales. And the power of martingales, as we've been saying, is that they're powerful results that you prove very cheap. For a simple result like this. So we insist in the martingale definition that we want expected value of xn to be less than infinity for all. That we'll insist. But we're not insisting this thing. That may not be. But just a simple condition like this tells you that xn converges to x. And there exists an x. So the xn converges on. Enormously remarkable result, right? How simple it is. Just with this condition, you get this.
Without the soup condition.
Huh?
Without.
No, without the soup, you don't get it.
Sorry.
Yeah, with the soup condition, yeah. So this is not going to be true typically. But if it's true, you get this. That there will exist a random variable x, and you get x and converges x almost. See, we've seen that getting almost sure convergence is hard. The law of Tarkov and all that. We showed you only the fourth moment condition. In the first moment condition is the fairly lengthy. Of course, with Martingale, we'll come up with a much simpler. We'll have some more machinery.
But you also told that for C plus epsilon movement also we can find this stuff.
That we had for dominant, that we had for uniform integrability, right? Is that what you mean, or?
It's not only the fourth movement, but if you just go for 3 plus epsilon.
No, oh yeah, you're saying we could have the same argument would have got
Yes.
possibly. Yeah, I don't remember, but that's we had that summation, so that would have summed up even for 3 plus epsilon. True. We have not been taking it that time because you can even getting it down to second moment is not so hard. Slightly, but getting down to first moment is much harder. So some examples of martingales, some straightforward examples. So I'll just say it because you know it. Yeah, support. Xi is equal to 0. So it's a simple, it's a 0 mean random walk and x independent. Only right. So is it clear that then okay, expected value of S of n given x1 to xn minus 1?
Is of
Yeah. Just Sn minus 1 because you take out what you know. We did that earlier, right? Both conditional expectation have this property in generality. Then given all of this, we can just take out Sn minus 1, we know it. And then the remaining thing we have okay, Sn minus 1 plus E of xn given x1 to xn minus 1. And we must have done this that if this is independent of that, then this is just E of xn and that's 0. So this is one martingale. Let's carry on with the same theme. Let's look at this martingale. Mn equal to Sn minus n times sigma square, where sigma square is equal to var xi. So I'm now assuming that all the xi's have the same variance. Okay. Otherwise, you can imagine this would have been just summation n sigma I square. Nothing more. It's not a big deal to find out. Okay. Can you see that this is also Martingale? This requires a bit of Sn square. Huh? So this requires a little bit of work, right? This is kind of spell out. Let's do that quickly. So -1. What do I do now?
10 minus 1 plus x and
And now you see, okay, Sn minus 1 square will come out. The cross term is going to be mean 0. Then because Sn minus 1 is known to us, and E of xn given everything is 0. So that's means 0. And then you have and then you have U of xn square, which is a sigma square. You get Sn minus 1 square minus. Right. Okay, let's look at some other martingales. Any martingale that comes to your mind? Do you remember?
take any random variable x and the sequence y1 y2 y. Let's say the equals to expectation of x given y1
Yeah.
do.
And then is equal to Q of x given. Let me do that later. Let me use sigma algebra before I define that.
Another can be constructed by two.
I guess what he's saying is, suppose I have a sequence of random variables y1 to yn on my probability space to all n, and I have a random variable x. Then let's look at conditional expectation of x given y1 to yn. So this is like our best guess for x given y1 to yn, right? On the sigma algebra of y1 to yn, we have projection of x. We already defined that. It's our best guess for this. So this best guess is improving as you get more information, right? But so that is a martingale basically.
So another one. If any random variables groups also creates a martingale, right? Groups decomposition.
Okay. Do you remember the group decomposition?
Yeah, some an plus mn where mn is
We'll come to it at the right time.
yeah,
Yeah.
it's a tricky one actually.
Yeah, no. And is this you can just see now, right? It's expect what do you want to show? We want to show the expected value of n plus 1 given y1 to yn is equal to
n plus 1.
no. That's what you want to show, right? Then it'll be a martingale. And then plus 1 we just plug in the value, so it's e of x given y1 through yn plus 1 given y1 through yn. Right? So this is the equal sigma algebra, the sigma small sigma algebra. So we know that this is equal to e of x given y1 through. So all the properties that we've seen of conditional expectation become useful immediately when we have martingales. This is the towering property. But let me give you example which I had in mind. I was hoping you would tell me, but I is non-negative, independent, you have xi. That's quite straightforward, right? Product of independent random variables all the mean one. That's clear. I don't have to do
Is
it.
it exponential of
Huh?
Is it exponential of
That's right. That's right. Yeah, I mean, that's my next part, that you can always take any random variable, exponentiate it, and then you can get this basically, if you do things the right way. I mean, you've seen that it's an important tool, right? Comes up in Java, bound how many places. But then anyways, for now, everybody agrees that this is a martingale. Sunanda, do you agree? Yeah. Okay, so this is good. Now we do what you're saying. Let's look at xi to be equal to e to the power theta yi. This will not be mean one random variable, right? So we normalize it to make it mean one. We put lambda I theta, where lambda I theta is log of e of theta y. Now, for this to work, this should be finite. Otherwise, the argument is there are many variables for which this is not finite. And for many variables, finite only for some theta, not for all theta. So that one has to be careful. So let's assume it's finite. Then this will mean one, right? And then you get, okay, your mn is equal to e to the power theta summation yi I equal to n minus summation I theta I equal to n. And this is good. And this is a nice martingale because you have e of mn is equal to 1, right? What can you say about scoop and e of mn? 1. That's also good. So you will get almost a convergence for sure. This martingale here. And you have a flexibility of choosing your theta. So in practice, you've probably seen in some application, you choose your theta as this equal to 0. E theta star summation yi. So it becomes a tool of kind of handling the distribution of summation yi. So we see that when we do large machine theory. Right? Okay, so now let's just do a formal, we just present things in some more generality, everything and more formally. So we need the, we are given a space UFP. We need the idea of a filtration. So you're familiar with filtration idea? So it's just a collection of sigma algebras. So each Fn belongs to F and it's increasing. So it's a sequence of increasing sigma algebras, right? All of which belong to F. And that's that collection of algebra, sigma algebras called a filtration. Generally, when we talk about Q of X given G, the good interpretation of G is G is a measure of information. So each sigma algebra contains some information. So for example, if G is sigma y1 to yn, it's like saying that I know random variables y1 through yn, right? Now what's my best guess for X? That's the interpretation. That's the information I have here. So bigger the sigma algebra, more the information that I have. So that same thing is being captured here. This is an increasing sequence of algebra. Then the canonical example is sigma x1 to xn equal to. That's what we've been doing so far. So as n increasing, we know more information. Okay, so now we define filtration. Let's define. We'll say sequence of random variables xn are let's call this X, adapted to Fn. So underlying assumption is that we're just talking about the same probability space. Everything is in UFP, all the Fn's are subset of F, all the random variables are defined this. Are adapted to Fn if Xn is measurable with respect to Fn for all this. So we'll assume this. So that's another definition that we have. Now we are ready to define martingales. So M equal to Mn is martingale with respect to filtration. It's always with respect to filtration. So hence your point that okay, you may be a martingale with respect to one filtration, but not with respect to another filtration. If M is adapted to measurable with respect to Fn for all n, and expected value of n is less than infinity for all n. This is the condition. Third is the weak condition, of course. Expected value of n plus 1. So typically we start with M0, and typically M0 is going to be a constant. You can say everything with M0 being a random variable. No problem. Typically M0 is a constant, and that is what is true. One more show you. And that's a micro. Okay, so that's all we need. But basic condition is this with adaptability. Okay. So now you can see, okay, you know what we had said earlier, E of X given Fn. This is a martingale, right? I mean, I just need E of X to be less than infinity, and then I'm set. Because I know that expected value of Mn is expected value of. Why is this finite?
This is E of X. This is E of X.
This is not E of X. This would be E of X if the absolute value is not there. Yeah. But it's
In decomposing into positive parts and negative parts.
why is this finite for Vn?
Suppose this is infinite, so either E of either E of X is plus infinity with non-negligible probability, or X is minus infinity with non-negligible probability. And then the first condition is
So you're saying that suppose this is not finite.
yes,
You go with that argument.
yes.
Now I can give you a random variable whose expectation is infinity, but the random variable is finite. That will not work either.
We can use the tower property as well.
Tower property doesn't quite work. It's absolute value of
What is tower property?
Tower property is the says that your expected value of x given g given H. When G is bigger than H, H is smaller than G is equal to. Tower is being reduced. Not very sure.
So you have given more.
Huh? Yeah, well, what you should use is.
E of mod x is equals to mod of x.
That's it.
Right, and then you start.
Jensen's, conditional Jensen's.
Conditional
Conditional Jensen's. Yeah.
And then that our property
E of mod x is.
less than equals to greater than equals to mod of dx.
Yeah. That will not be enough, right? That will not be enough.
We can do it like this.
Right, this absolute value can take it inside. So E of x given Fn is dominated by E of absolute value of x given Fn. So E of x given Fn, the absolute value, is dominated by E of absolute value of x given Fn. Then the expected value of that you get. So this is from Jensen's. Right. Good.
How immense?
Yeah. Oh, no, yeah. Yeah, so good. Okay, then how do we define super martingales?
Is less than equal E of x plus 1 given if less than
Yeah, so super martingale is actually decreasing on average. Sub martingale is decreasing on average. You know why that happens? This super martingale?
it's just naming.
Huh?
It's just naming.
Yeah. So why was this naming done? So all of this is done by JL Do. He defined a martingale, he proved the main theorem, he did everything in martingale.
This was denoting loss.
No, this, so it's a little deep thing, I won't go into it. If you were to write, Ito's integral of function of B, then you get this kind of expression in terms of harmonics and subharmonics of F. So for any function F, this is called, it's called harmonic function if del F is equal to 0, F is a function of x1 to xn. This just means you know what this means?
Yes. Super one.
This just means summation, I guess, del F, del 2 by del x I squared. So if this is equal to 0, it's called harmonic. This is greater than equal to is called super harmonic,
And less equals to
because subharmonic.
and that is just here it is the ultra.
Yeah, well, when you represent a martingale in Ito setting with function of F, you get for super martingale, this will be, if this is positive, you get a super martingale. So for a super harmonic function, you get a super martingale, for some harmonic function, you get a sub martingale. So that's why you call it super martingale. Still seem like lacking common sense. In martingales, it should be that super martingales are increasing with n and sub martingales are decreasing with n. That would be a much more common sensical thing to do. But they're not going to do that. Okay, so let's carry on. Yeah. So then we can get kind of new martingales from old martingales. New betting strategy from old betting strategies. So you kind of so we define one more definition. Sequence of random variables an is called P visible or non-anticipative. If we again on UFP probability space with a filtration Fn, if En is measurable to Fn minus. So it's known to us just by n minus 1 when we know Fn minus. We know what it is. Right. So it's obviously adapted, but it's more than that. Fraud. And now you can define new martingale. So you can define yn is equal to summation ai mi minus mi minus 1 I equal to 1 to n. So suppose mn is a martingale. Okay, so these are kind of zero mean increments. You can check whether these are uncorrelated increments. Huh? So for any martingale, the martingale differences are uncorrelated, but need not be independent. A very simple example of random variables which are uncorrelated but independent. Very easy to check this. So these are the bets that I'm making in a gambling. But before I play the gamble, because I'm at time I minus 1, I'm going to play a gamble, and this is what my winning is going to be, which on average is 0. I ramp up my bet by AI, which I know at time I minus 1. Because so beforehand I ramp up my bet, so I don't lose the zero mean property because I'm not seen the outcome. And then what I get is again a martingale. Yeah, why? Let's just check. First of all, why would this be true? So this is called the martingale transform of AI with respect to this quantity here. What's nice about this is that you can almost immediately see that. So this is like a discrete transform. In the continuous time, this will be an integral with respect to the martingale. So whole of Ito's calculus, stochastic calculus is based upon kind of integrals of martingales and semi-martingales and all that kind of stuff. Extremely elegant theory. And quite important. So you talk to people who are experts on continuous time or this kind of stuff in detail. They think everything we do with this discrete stuff is baby stuff. They don't even want to talk about it. So the tools and techniques that you need get further.
Isn't the iteration is continuous in that case or like means?
What's that?
Means in the continuous case, is the iteration of the filtration you are taking,
Yeah,
that is continuous also. It's like if any in between any n plus some you will get infinitely.
yeah, it's indexed by t, which now t is a time. It's continuous.
Example of the sigma algebra that has.
Well, we do all of this, but you know, when we do Brownian motion, that's the smallest sigma algebra which makes the first t variables of Brownian motion measurable. It's a very natural thing. You can't avoid it. When you do Brownian motion, you have to learn this.
That's the basic one.
Yeah. That's the starting point. That's the kind of, I guess, Bernoulli distribution. It's interesting because mathematical finance community kind of just starts off with that. This finance is all kind of modeled as continuous time processes. Having said that, I guess physics also should be, you know, all the temperature, pressure. If you were to model, for example, how climate evolves, it's evolving in continuum as a function of time, and it's not a one-dimensional process, right? It's probably much more. It's a field. Oh, this is very essential.
So one thing, so whatever the model you are talking about,
Yeah.
so don't we also need to agree or some data where you are starting point at 0 and basing up to the data up to n, we are trying to predict the n plus 1, but don't we also need to see that the past one, means in the past time, -1, -2, that will be also equal, is same in the data plot. Because I'm trying to say that can we increase the multiple in the backward way somehow?
Yeah.
Means that there is a concept of reversible Markov chain. So that we can talk about up to -7.
You want to rewrite history,
No, not rewrite.
not rewrite history, but that also gets done. But you at least want to model history. Yes, x0 is what's happening now. You want to say x0 came from some process.
Yes.
Yeah. I mean, okay, so I don't want to comment too on it because it's too vague right now what we're discussing. But certainly when we fit a stochastic process, xn, you know, every time we say we have a stochastic process, xn, we give some properties, for example, okay, xn is a times xn minus 1 plus b times some IID variable Gaussian. That's a very standard way of doing things, right? So this is how I define this process of the IID. Now the question is, okay, I'm saying that somehow a real world phenomena fits this, follows this kind of property. So the question is, what's a good A and what's a good B, which explains this? So that's where statistics comes in, where you fit a probability model. Statistical inference, you're inferring from the data what the underlying model is. And that's where you look at the past data. But once you've done that, you say, okay, x0 is known to me, it's an observed value, so then I don't have to worry about what happened before that.
I see.
I'm assuming it's a Markov process, so given x0, what happened before that is not important. Right. There's this whole thing about like in the real world, how do we count the stochastic process, right? So you propose some structure, then fit it to data. But reversible Markov change is something else, right? It's just saying that you look at the stochastic process forward or backwards, probabilistically you're looking at the same thing. Then nothing is changed. Okay, so this Yn we want to show given Fn. Fn now is the Fn is a sigma level so that Xn is Mn is adapted to it and AI is pre-visible with respect to it. So why is this a Martingale?
The expectation of AI into AM plus 1 into Mn plus 1 minus Mn is 0.
Yeah, it's better to look at this quantity here, right? The difference. And you want to show that difference is 0. And that's your point that is equal to P of, I guess, A plus 1, n plus 1 minus Mn. Fn. N plus 1 is known to us given Fn. It can be taken out. And then what's remaining, we know it's a Martingale with 0. What's missing right now is, okay, we still have to show that expected value of we are given Mn as a Martingale, so this we do know. So one standard way is you just assume that your AIs are bounded. Then this follows. Okay. Otherwise, you can assume that your MNs lie in L2 and your AIs lie in L2, and then that Cauchy-Schwarz you should be able to show this. Because this variable here, each increment here, and these two variables here, I can apply Cauchy-Schwarz to them, right? Second moment of this is finite. Second moment of each of this is finite, and the difference is also finite. And then you can go for each n. Any given n has to be finite, not a supreme. So that's what we are going to assume that we'll assume either we have second moment property in L2 or the y is about it. But it's very good, it's very powerful because now we can use an old Martingale and construct many more Martingales. And you know, you can do this again, right? I can now put in Yn there and can construct with one more process A prime and Zn and so on and so forth. So with stochastic integrals also you do this. Stochastic integrals are Martingales, and you can have integrals with respect to those guys, and they're also Martingales. And you can ask yourself, okay, what happens to this as you carry on? So all of this leads to interesting words. Okay, right. So now let's talk about stopping time. So random variable tau And what we have is the back of our mind is mu f of filtration Fn and a probability space. Okay. On this now we're going to define a random variable tau. It's called a stopping time. Anyone?
Tau is integer where positive integer value then predictive.
It takes values. 0, 1, 2. And you also allow for plus infinity. Oh yeah, up till now we've just been careful. Everything we define, we could have defined out plus infinity. So it takes values these and then
And the event tau in less than equals to t is if t minus one predictive.
so whether tau is less than or equal to n or not, I can say convincingly by observing the underlying Fn, information of the Fn. So Fn, for example, if it corresponds to x1 to xn, just by observing x1 to xn, I know whether tau has occurred or not occurred. Have I stopped or not occurred? I'm unambiguous on every part. It's not like I'm not sure. That's roughly what this intuitively means. Right? So the example is, okay, what is not a stopping time? So they say, okay, when do you stop toasting the bread? When you kind of open the, when do you stop the toaster, just heating the bread? It's like 2 seconds before it turns brown. That's not a stopping time because it's already, it's not, you have to look in the future to decide that. So this is saying that, okay, this information is available to us in the past itself. So for example, suppose I say soup and what about this? It's an endless component.
So the thing, the system that you kind of observe directly by your hands.
No, I completely forgot what I wanted to say. Just give me 1 second. This is what is giving me an example. Let me first give an example of a stopping time, then I give an example of something else on stopping time. So what was the point? Was
So the system where you cannot take the data directly, directly from visualization. For in that case, you are getting non-stopping time examples. Is it?
so the point, so your question is where are we going with these stopping times?
Yes.
And how are they useful, for example? So the big picture is going to be that, when I gamble, for example, and I'm observing, suppose my best process is a martingale. And in an ideal world where each gamble is a fair game, not realistic at all, right? But in that world, I implement a stopping strategy where I say if so far I'm winning, so much after, as soon as I win 40 rupees, I'll stop. Or as soon as I lose so many rupees, I'll stop. Or if I see a particular pattern, I'll stop. Right? So my stopping time now is a random variable. It depends upon whatever I've seen so far. So that's what I'm trying to capture here. So I'm trying to capture the quality M of tau. Martingale observed at a random time. And the big theorem we prove is that E of M of tau, because tau now is not independent. When I stop, it's not independent of what's happened so far. It just depends upon everything that's happened so far. And I'll prove that this is going to be equal to M of 0, which we get equal to 0. Right? So we'll say under general conditions this is going to be true. And sometimes it will not be true. So we'll highlight it.
Tau is bounded.
That would be one condition. That would be one condition. So that's the kind of game that we are trying to achieve. We're trying to say what happens if you have a sequence of random variables and we stop them at a random time. What's fascinating about stopping times is that when we go to the continuum, we run into all kinds of unseemly technicalities. Because up till now, because we know that if A1, A2, A3 are probability 1 sets, then so is the intersection. Countable intersection is also probability 1. Countable union is also probability 0 for each one is. No longer true in continuum because all of these are uncountable unions and uncountable intersections. So all kinds of technicalities you have to kind of deal with all that stuff, and then stopping times become your vehicle to kind of conquer continuum. So that's the other utility of stopping times. Okay, so one stopping time can be okay. Tau is first time infimum n does that, and then is given equal to, let's say, some number. Okay. So then, okay, tau less than equal to 25. I'll observe M1, M2, and 25. I know whether it's in 25 or second. Collect, and if I look at the set tau less than equal to 25, let's say, I can write it down as a function of M1, M2 to M25. So it will be in F25. When F25 is, M1 to M25 measurable, so F25. Being a little bit ambiguous right now, but you get the idea. So this is an example of a stopping time. So now, yeah, I guess if I say supremum n less than equal to 100, and then is greater than 40. Now this is not stopping time. If I see up till 90, I can't be sure that that's the last time I'm going to be crossing 40. I have to look in the future. So what's nice about stopping time is it's capturing realistic strategies that we implement. That's because we're not allowed to look in the future. That aspect is captured very well. So again, very useful in finance where you're doing investing in a variety of securities, etc. You can't look into the future, or at least if you're unless you're working for a really expensive brokerage firm where you can kind of do insider trading. Most of us cannot look into the future. You know what Rajat Gupta at all? Or? You know what Rajat? Yes. Harshman, yeah, well, that was different. Rajat Gupta is more interesting. He's you compare everybody else to him, you compare everybody. But he's he was engineering student from IT and all that kind of stuff, and then he was head of McKinsey worldwide. And McKinsey, do you guys know it all, or
Is consulting.
but it's kind of the most kind of Brahman of all the consulting firms.
Asset management.
It's strategic consulting. I mean, they generally go to a company and give them a hawk-like view. You should not be in this business, you should go in this business, and this is how you should start the business. Strategic kind of big picture that CEOs want to listen to. And now I'm talking about companies which are like 400,000, 500,000 employees. TFR is 1,500. So, it's a very big company. So to guide them how they do that, they hire bright youngsters, they capture data worldwide, they do analysis and kind of make a story out of it. So it's a very well-regarded firm, which takes itself very seriously. And yeah, if you're a CEO of that, you've generally been kind of, you're a strategic thinker, which is well regarded worldwide. And how I know him is because I used to attend his talks every now and then. Used to be there. So he used to give all these kind of talks about helping India and all that. So he started Indian School of Business right now. That was something that he started. He got people. He first came to IITs and wanted to set up a management school there and realized it's not getting anywhere. So then he started ISB, and he wanted to start a public health institute. Public health institute, that's clearly important. So very well-meaning guy, but this is, I guess, in the early 2000s. The story is that he was a kind of a multi-millionaire who was hanging out with multi-billionaires. So he wanted to be a multi-millionaire. So in any case, long story short, he was in a meeting, and quickly after the meeting with this is Goldman Sachs or something, he made a phone call where he told a hedge fund guy, God knows what he said, but the phone call happened. And apparently then FBI was paying attention to what he was saying, and he had to go to prison. This was insider trading. So it's like In a meeting, you hear that this company is going to do something, and then you tell somebody to buy and sell accordingly. Sorry, it was a big story.
No, why is it illegal?
Huh?
Why is it illegal?
That's illegal, it's insider trading. Because you know something you have unfair advantage.
I should be allowed to use my unfair.
Huh?
I should be allowed.
But then the people will lose faith in the system, right? Then nobody else will invest.
In the worst case, I should be banned from trading.
No, I mean, the only way you prevent this is by having strong guarantees. Otherwise, people will keep doing it. This is all about how people behave, right? So if you allow insider trading, people stop investing in the stock market. In stock markets, you need people to invest because that's how corporations raise money. That's how productive activity gets done. New projects get launched.
No, you just stop, freeze his stock accounts. Freeze his email.
No, but that's not enough. So it's true. What is the right narrative? So anyway, his strategy was not so bad. I think it was only 2 years in the year. And then life of infamy thereafter. Yeah, so I started all this by saying that you're not allowed to look in the future. That's a stopping thing. Okay. The stopping time is kind of crucial to one of these things. All right, where do you want to go from there? So we define stopping time, all right? We define it precisely. Now we define a stop process. So we say M of tau. So M of tau is exactly what you expect it to be. It's M of n indicator. Tau will be n. And that's what M of tau is. This is a stopper. This is a stopper. This is random variable M observed at tau. Random sequence M observed at tau. I also define M of n min. So this is equal to M of tau if tau is equal to n. M of n if
In this.
tau is. So this is called a stop process. So stopping time, but I stop it. And what we'll see is that if Mn is a martingale, then the stop process is also a martingale.
So you can only function, right? Yeah, Martingale. Okay, is a Martingale you can only for every stopping time.
Yeah, that's true. That's true. We won't go there. I mean, let's do the first level things in this course, otherwise it's not very interesting thing, I can say. It's a very nice book which I really like. I can't tell you what it's right now, but it's kind of connecting martingale and stopping times to flows and cuts in graphs. Right, so that was kind of a very neat use of that. So you connect some problems in martingales, which is kind of, I think, all the strategies which are available. Suppose if you implement strategy tau, you get a payoff E of n tau. Let's say. And now you're looking for all possible tau which are available to you. Tau beyond some set t. Okay. Yeah, so these kinds of quantities you can relate to max flow problem solving these. Stopping time you think of as cuts, and martingale you think of as flows. Nice, elegant work. I mean, it's also nice because you have to wonder when you tell us that you have a great algorithm max flow, almost linear time, right? So you have to ask yourself, how would that generalize in this setting? Because you're saying the same thing, but in a more general setting, so you can have implications. All right. Yeah. So why is that the case? What you do is you just take your A of t to be indicator that, or A of n, let's call it. Tau is given to n. Okay. So A of n, this defined is bounded. So that's fine. And now you know that okay, tau greater equal to n event is basically equal to complement of tau is less than equal to n minus 1. and this belongs to Fn minus 1. Right? And hence summation A t, let's call it, mt minus 1 t equal to 1 to n. Let's call this it's a martingale, and you can just now look at this. So this is exactly equal to n tau min minus m0. M0 is f0 measurable. So if mn is a martingale, mn minus m0 is also a martingale. In particular, if this is a martingale, this plus m0 is also a martingale. So this will be a martingale. So stock processes are martingale. Right. By the way, the stopping time is defined as tau less than or equal to n in Fn, right, for all. You can check that this is same as saying that tau equal to n is in Fn. So, can you check that one implies the other?
Tau less than equals to n minus tau less than
Tau less than minus 1. That's right. Yeah. Right. If this is in Fn, then this is just a union of these guys, right? Yeah. This will also be in Fn. If this is in Fn, this will be in Fn. This fact is not true in continuous time. So that's why one goes with this definition. All right, let's do something fun. So for one fun thing, suppose I give you a random walk. We have to do 2 complex. You already know the answer of this thing, now we should rigorously. Sn equal to summation xi I equal to 1 to n. Xi is plus 1 minus 1 with probability half it. Right? So this is what's called a simple symmetric angle. Simple because it's plus 1 minus 1, symmetric because it's mean is 0. Okay. So now I give you, okay, A and B are integers greater than 0. And I say, okay, tau is equal to infimum n such that Sn is greater than equal to A, Sn is equal to A, or Sn is equal to minus B. I start with 0. So first time either I hit level A or I hit level B. Okay. And now I want to find the probability that S of tau is equal to A. We started the course with this in the running motion setting. But what's the guess for this? B upon A plus B, right? So now I ask you to prove it.
So, by optimal stopping period, the expected value is 0.
But we've not done this topic yet.
No, but does the theorem we just mentioned? E of tau, E of x of tau is 0.
So S n min tau is a martingale. One thing one should know about martingales is that okay, I have mn plus 1, E of mn plus 1 given as Fn is equal to mn. This immediately implies that E of n plus 1 is equal to E of mn. The expected value of all the random variables are the same. Okay. So this is a martingale that we discussed. Right? With Sn is a martingale, so this is also a martingale. That was the stopping time. What can you say about this? What happens with this as n goes to infinity? There's no big thing. But that's because, and why is this true?
The tau is less than infinity, probability is 1.
Yeah, so you need that. You need that the probability that tau is less than infinity is equal. Then on every omega, eventually you're going to hit tau in the stop. Hence this is happening, right? And this has to be proved. It's kind of easy because you're starting at 0 after some number of steps. There's a positive probability that either you cross A or you come down below B. Suppose that doesn't happen, then after that number of steps, no matter where you are, there's a positive probability. So you can build a geometric argument to tell you for sure you're going to cross it.
Just showing greater than 0 will be enough.
Just doing.
But just showing it is strictly greater than 0 will be enough.
So I missed the.
Just showing that it is greater than 0.
Yeah.
By 6.
Yes. Right. So this has to be shown, but it's kind of straightforward. Or if you want to be more complicated, you can go ahead and tell you. With geometric argument will work. Okay. So this is not work now. So this is going here. Now what do we do?
You know E of S of n minimum n and tau is 0.
Yes, we know this. That's
Dominated convergence theorem has n goes to infinity.
right. So S till time tau, this guy is between A and minus B. So it's a bounded process. After that, A not B. So it's dominated till that time, so I can use dominated conversion. Because of random variable is dominated, so I get E of S n min tau is converting to E of S tau. But what is this guy equal to on the left hand side?
Limit this is 0.
This is always 0. This is equal to E of S0 min tau, which is S0, which is 0. So this is always constant. So if I tell you that a sequence of constant numbers is converting to something, then that something also has to be the same constant. So this is a kind of a roundabout way of proving that E of S of tau is equal to 0. Okay. Now we know this. How do we exploit this now?
The probability is P and this is P plus 1 minus
So this is exactly, it's A times probability that S tau, because S tau takes only two values, right? S tau is a nice random variable which takes only two values, A or minus B. A is probability that S tau is equal to A minus B into probability that S tau is equal to minus B. And this is just 1 minus the probability of S tau is equal to A. This has to go to 0, implying that probability that S tau equal to A is equal to B upon A. Right. Okay. Now suppose I want to find expected value of this tau. Remember we discussed this also in running motion. Do you remember what we said this was equal to? We had said that this was equal to, interestingly, A times B. It's not such a, I remember thinking about this, I didn't have a clear intuitive argument as to why to expect this. You say it has, okay, maybe if I double B, then this should double. It's not so obvious to me that that should happen. But double A, yes. But intuitively, I can't convince myself that that's the way it should be. And I can't say, okay, when I start from here, I come there by, just by saying I'm independent thereafter. So maybe there is actually, but I just didn't. I remember I was not convinced that I had it out.
So your SI mn square minus n sigma square, that is a Martingale.
So now that's how we prove this. So this is the power of Martingale, and you can show these things quite cheaply. What we'll do is we look at mn is equal to Sn square minus n. Sigma square is 1. Xi just takes value plus 1 and minus 1. So what's nice about this formula is you can isolate n. So if you stop at tau, you can isolate tau. Because now what we'll do is we'll argue that okay, n min tau is also going to convert to m of tau. Same with tau, right? And it's bounded. So I get that okay, E of m of tau is also going to be equal to 0, right? Okay, so I have E of S tau square, E of tau, right? And this I know, this is just A square into B upon A plus B plus B square into A upon A plus B. And that gives us equal to A. And that's equal to it. So anyway, so let's carry on doing fun things. The next time we'll do a few more examples with martingales. Then we'll do the martingale stopping time theorem. Remarkably easy thing to prove. Then we'll do martingale convergence theorem, which is what I told you, soup, and if the martingale is L1 bounded, then it converges on the theorem. And that's a beautiful proof. Again, Duke's proof, which has a very geometrical flavor to it. Completely non-trivial again. Anyways, that's for now. I think with that will probably be the coursework for the exam, right? For the midterm.
After that, practical.
After that, so I was thinking first I do running motion and then large deviation. My heart is much more doing large deviations over running motion, but we can change the sequence if you want. And in between, we'll have two lectures on Shubhatra on week.
Sir, in the last step when we are applying the dominated convergence, aren't we assuming that tau is integrable?
We are assuming that no, all we are really assuming for that is this. It is integrable, but all we are assuming is this. All we need, this is some, I mean, I could have called this xn, this whole sequence. So all I need is the xn is converging to some random variable x. And then I told you the xn is bounded. That's all I need. Good, then
Okay.
yeah. So I don't need the p of tau equal to infinity. I don't need that. That would of course suffice. It's not needed. But when we do a more general stopping time theorem, then we'll have a condition where this is important. This is we discuss it next time. Okay, so any other questions or? But yeah, nowadays it's very hard to see any work in probability which is interesting which doesn't have martingales. It's too tough. And this is a process. I don't know anything very see. That's it. Quite amazing, quite remarkable that nobody expected this. Okay, Praveen, sure,